Welcome to Euler's proof, part 1. Okay, so I guess we'll start with the definition of E. As you recall, Euler is the one who first invented E, and he came up with the definition. E is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. Now, he originally devised this when he was looking at compounding interest, and he wanted to know what would happen if you compounded interest continuously. But he went on to think about this number that he had invented, E. All right, and I guess we should mention that this, when you put it in your calculator, for instance, ends up being like 2.71828, etc. So here's Euler's idea. This is just a binomial that needs to be expanded. So the same thing that we've been doing before with Pascal's triangle, corresponding to combinations, etc., could be done with this. The only problem is that we are talking about an infinite expansion. So it's going to get a little bit messy, but then some amazing things start to happen that make it all worthwhile, at least from Euler's perspective. So let's think about what this is going to look like when we expand it. We still need a limit all the way over here, and n is going to infinity. But let's not think too much about that infinity. Let's just think about what the terms would look like. So the first term is going to look like nc0, that's the coefficient, times the first term raised to the nth power, times the second term raised to the 0. All right, then we've got another term, which is going to look like nc1 times the first term raised to the n minus 1 power, times the next term raised to the 1, and then another term that's going to look like nc2 times 1 to the n minus 1 times 1 over n squared, and so on. You get the idea. Okay, so I'm going to stop writing that limit thing over and over again, but now let's try to actually think about what all this looks like when you expand it, all right? So first of all, the combination of n things taken 0 at a time, that's just 1. And 1 to the n, that's also just 1. And then we've got 1 over n to the 0, and that's also just 1. So our first term looks like 1 times 1 times 1. Okay, it's not going to stay quite that simple, but not bad. nc1, all right, that's the combination of n things, choose 1. So there's n possibilities there. 1 to the n minus 1 is still 1, so I'm not even going to bother to write that pretty soon. Oh my goodness. And then 1 over n to the 1 is 1 over n. Okay, let's keep going. nc2, so that's n times n minus 1 over 2 factorial. 1 to the n minus, oh, there should be a 2 here. My bad. Okay, 1 to the n minus 2, I'm not even going to worry about writing that. Okay, but 1 over n squared, I think we should write that. And that's 1 over n squared. All right, and actually, let's add a couple more terms. So the next term would be n times n minus 1 times n minus 2 over 3 factorial times 1 over n cubed, and so on. I guess that's all we're going to fit there, on to infinity. Okay, so these first couple terms are pretty simple, but now things start to get a little more complex. So let's just examine a couple of these terms. And what I'm going to do, I don't care about the 2 factorial, because I know how to deal with that what I'm worried about is this n stuff. So if I multiply this thing out, I'm going to get n squared minus n, and I'm going to bring this denominator underneath over n squared. Okay, and then we'll put everything else over to the side here. So times 1 over 2 factorial. This next term, if I multiply that thing out, I'm going to get n cubed minus 3n squared plus 2n. I'm going to do the same thing here. So I'm going to bring this n cubed underneath. All right, and then I'm going to multiply this times 1 over 3 factorial. And we could keep going, but I think we won't. Okay, now remember, all of this is still inside of a limit as n is going to infinity. So what's happening to something like this as n is going to infinity? Well, remember, we just want to look at the largest terms. So that would be n squared over n squared, which is just equal to 1. So this thing is actually just approaching 1 over 2 factorial. What about this thing? Same idea, we just want to look at the largest terms here, n cubed over n cubed, there's our plus sign. So that's just approaching 1 over 3 factorial. Okay? And in general, right, suppose we had another term. Suppose we had gone to nc4. That would be n times n minus 1 times n minus 2 times n minus 3 over 4 factorial times 1 over n to the 4th. Well, the same thing is going to happen here. The leading term is going to be n times n times n times n, which is just n to the 4th, divided by n to the 4th. Those are going to cancel, and we're going to get 1 over 4 factorial. What about working backwards? Let's look at this term over here. The n's cancel, and we are just left with 1, which I think we could think of as 1 over 1 factorial. Well, if we follow the pattern backwards, then this first one should be 1 over 0 factorial. Remember, 0 factorial is defined to equal 1. And this thing equals 1. So we're good. All right. So this is pretty exciting. What does that mean? That means that E is equal to the limit as n goes to infinity of 1 plus 1 over n to the n, which we just expanded and found that that is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus dot dot dot, which we could simply represent as a summation as k equals 0 to n of 1 over k factorial. That's a very satisfying result. So that is it now for part 1 of Euler's theorem, and I think the next step is to go ahead and do the problems that correspond to that in the assignment sheet, and then we'll move forward with step 2 in just a moment.